If you have taken a course in trigonometry, it is quite likely that you have seen this formula before. It is often referred to as the sum and product formula, and here we give it as an example using the two sine functions. As its name tells us, it essentially claims that we can write the sum of two sine functions as a product of a sine and a cosine. If your teacher has taught you how to prove it, they probably started by writing the compound angle expansions of the two sines on the left-hand side. If we add these two expansions and eliminate the terms, we would quickly get something that looks very similar to what we started with. If we do a simple substitution in the angles, we would quickly retrieve our formula. This formula is really useful because it can be used to evaluate integrals of this form. But even though we finished a proof, it still seems quite amazing that we can write the sum of two sines into the product of two sinusoids. It is not at all intuitive that we can do this. So, why is this true? Can we actually write this using some geometric relationships? A common way of finding the geometric representation of a trigonometric relationship would to be converted to complex numbers. If we look at the definition of Euler's formula, it will not be hard to see that sin x is simply the imaginary part of a complex number with modulus 1 and argument x. For simplicity here, we would like to substitute x for omega t, which will make no difference. By using the substitution, we can think of sin x as the projection on the y-axis of a unit vector rotating at angular velocity omega. This method is called the method of phasors, and often we find the trigonometric relationship by considering the addition of vectors instead of the addition of trigonometric quantities. With our tools in hand, we can rewrite the left-hand side of our formula using phasors. What we get are two unit vectors with different arguments, omega1t and omega2t. If we find a vector sum of the unit vectors and take its y component, we should get what we have on the right-hand side. If we trace this y component, we get a quite strange looking curve, which does not match yet what we have expected. So, what can we say about the imaginary part of our resultant vector? As for any complex number, the imaginary part depends on both the argument and the modulus. Here, we should start by looking at the argument of our resultant phasor. Since we know that both our initial phasors are unit vectors, it is not hard to see that the resultant phasor must lie exactly between them by symmetry relationships. Therefore, the argument of the resultant phasor would be simply the average of the two initial arguments, which gives us omega1 plus omega2 divided by 2 times t. Then, what can we say about the modulus? We know that it is maximum when the two initial phasors are aligned, and it is minimum when they are opposite. Therefore, we would expect the modulus to go through a full cycle each time the faster phasor catches up with the slower phasor by one full circle, which would give us a dependence on omega1 minus omega2t. However, remember that each sinusoid function has two peaks, one above the x-axis and one below. Therefore, the true period for the modulus would be double than what we have, which would yield half the angular velocity. Therefore, we have this expression. Now that we have recovered our two terms, what we need to do next is to rationalize why we have one sine term and one cosine term. At t equals 0, we know that the argument of our final phasor is equal to 0. A 0 at t equals 0 would correspond to a sine relationship. Likewise, at t equals 0, the two initial phasors are completely aligned to each other, which would give the maximum in our modulus. Therefore, the modulus dependence would be a cosine instead of a sine. The final detail that we need to sort out is why we have the coefficient of 2 in front of the two terms. When the two initial phasors are aligned with each other, their magnitudes add up, and therefore we have twice the initial magnitudes. Now finally, we have what we started with, the sum to angle formula. So, What would our function look like if we plotted it out on a graph? What we get is a sinusoid that oscillates between another sinusoidal envelope. The envelope comes from our modulus term as it oscillates at a much smaller frequency. The oscillating function that is enveloped inside comes from our argument term. Therefore, we can easily see how our sum to product formula is actually correct.